Hello, GameStack Live. Wherever you are in the world, welcome. It's awesome to be here with you today, even if it's only virtually. Of course, whilst you're watching this video, it's probably raining outside here in Seattle, so maybe virtual is for the best. I'm Simon, and I'm a member of the DirectX team here at Microsoft. It's my privilege to talk to you today about how we're improving high dynamic range support in DirectX games. Now, this is a Windows and PC focused session, but most of the information also applies to Xbox, and many of our best practices can also apply to any cross-platform title. So we have a full agenda for you today. We'll start with a quick update on how ecosystem adoption is going with HDR in Windows. Then we'll dive deep into the display hardware portion of that ecosystem, looking at the recent work that Microsoft is doing to improve the quality of HDR displays. Then we'll go into a lesson about how your game can take advantage of Windows system capabilities and tune your content to optimize for a particular HDR display. And finally, we'll cover an exciting new technology, Auto HDR, that we've recently announced. You'll learn what it offers to games and how you as a developer should think about it. Okay, let's dive in. So we first shipped HDR support on Windows 10 back in 2017, and we've come a long way. We've steadily enhanced support in the operating system, and we've been super impressed by the progress across our ecosystem. This includes graphics silicon partners, PC manufacturers, and of course, developers like you. So first, we have games, with over 130 titles using HDR in Windows. Just looking at games published by Microsoft, we see beautiful HDR across all kinds of art styles and gameplay genres, including Flight Simulator, Ori and the Will of the Wisps, and Gears Tactics. Moving on to hardware, we have over 250 certified laptops and monitors from every top PC and monitor manufacturer. I'll talk more about what display HDR means for you later in the session. And last but not least, here are over 9 million HDR-capable PCs. This population has been growing by 3 times every year over the last couple of years. This means a PC meeting all of the system requirements to run HDR, including an HDR display and a GPU. Even more impressive is the number of active engagement hours. This has been going up by 4 times year over year. At the bottom, we have just a couple of examples of new HDR gaming laptops and monitors that were recently announced at CES. By the time you're watching this video, these should all be available on the market. So personally speaking, it's really exciting to see HDR support start to cross over from the premium and enthusiast market segments into the mainstream. But at the same time, we know that doing HDR the right way is hard. So I want to frame the rest of this session's contents in terms of the top challenges that you have been seeing and how Microsoft and Windows are helping. First, when we talk to developers and users, by far your biggest concern is that HDR displays just have so much variation in their performance and image quality. One of the things that Windows can do as a platform is to work with the entire ecosystem to raise the consistency of new HDR displays. When your game is actually running on a gamer's system, we'll teach you how to extract the maximum image quality from their display. And finally, we strongly believe that HDR is the new standard for any high-fidelity game. But let's say you're working on a game with existing engine or existing art assets, and the upfront investment needed to upgrade is just not an option. In these cases, Auto HDR provides a great bridge for your already shipped code to gain many of the benefits of HDR. All right, first on the list of challenges is HDR display quality. For those of us who are immersed in the world of consumer HDR, it does sometimes feel like the Wild West. For starters, HDR displays have a huge dynamic range of price and performance, no pun intended. You can have a budget HDR monitor that barely hits 200 nits of peak luminance, and this is no better than a traditional display. And it can sit right next to a mini LED prosumer monitor that can get 1400 nits, over 7 times the brightness. Yet both of these displays can claim to be HDR10 compatible. What's worse, once you try rendering to a display, it may do anything and everything to your color values. This ranges from distorting the hues to being too dim or too bright, or any one of a number of possibly dubious image enhancements. And of course, when your game is running on a PC or console, you have no way of actually knowing what's going on at the other end of that video cable. So this obviously wreaks havoc with the color grading and artistic intent that your team has carefully defined, but can also break your gameplay. Imagine you're playing a competitive multiplayer shooter and you're inside a building and you're looking out a window at the bright sun. On a poor quality HDR display, this is going to clip the entire scene to white. And so you literally won't be able to see your opponent who might be facing you with their gun ready to shoot. And finally, when your customers or even members of your own studio ask what HDR monitor they should purchase, it's really hard to provide a good recommendation. Microsoft's approach is to partner closely with the industry to promote and develop HDR standards and certifications. This includes groups like VESA Display HDR, which will be the focus of this session, and the HDR Gaming Interest Group. We want as many manufacturers to be able to participate as possible, and therefore our specs and programs are vendor neutral and open. As I noted before, every major PC manufacturer and monitor manufacturer is building display HDR products today. Looking at the standards themselves, we were laser focused on designing them to ensure a high quality end-to-end user experience. On display HDR in particular, this means it requires accurate and consistent color reproduction and capability reporting. And this helps to guarantee your game's artistic intent and gameplay are preserved. Now, we also want to promote innovation, where manufacturers compete to raise the performance of their displays and provide users with a superior user experience. Here are some example display HDR performance tiers. Each tier defines a comprehensive set of image quality requirements. This includes static contrast, color accuracy, gamut, and bit depth. But for consumers, they get a simple message. They look for a higher number as better. The numbers here represent the peak luminance of the display in nits, which is the most prominent and intuitive measure of HDR performance. In addition, tiers like True Black showcase the strengths of OLED and self-emissive panel technologies. Their peak luminance is more limited than other tech, but they offer superior image quality in dark viewing conditions. So to recap, thanks to our efforts, certified HDR displays will just work. Of course, in the next section, I'll cover some best practices for your game to optimize for HDR and also how to handle non-certified displays. For purchasing guidance, Microsoft strongly recommends consumers look for a certification like Display HDR. This guarantees you'll get a baseline of quality, and based on your budget, you can then choose a performance tier to match. Now, there are other HDR certification programs run by our silicon partners. This includes AMD FreeSync Premium Pro, Dolby Vision, and NVIDIA G-Sync Ultimate. These programs are great too. Broadly speaking, they have similar goals and requirements, and in fact, most models are also Display HDR certified. And finally, if you're looking for a color grading or mastering display, we specifically recommend a Display HDR 1000, 1400, or higher tier. These are capable of reproducing the colors from the vast majority of consumer HDR displays out there today. All right, so as I just mentioned, even with certified HDR displays, we still have best practices you should follow to give your HDR game the best possible experience on the hardware that your gamers are using. HDR calibration on displays is a pretty deep topic. So I've organized this section into tiers: good, better, and best. Each tier involves incrementally more work over the previous tier, and in return, you'll get a superior user experience and image quality. Good, you're simply using the operating system APIs to get the calibration data Windows already has, for example, for a certified display. Better is about supplementing that data for displays that aren't certified, so you guarantee a consistent experience across every kind of display your users may own. This is especially important for HDR televisions, which are very common and many of them don't follow any HDR certification. And finally, best is about providing the additional knobs and settings so you can extract the maximum image quality out of the user's display and specifically optimize for your game's content. As a note, in this section, I'm only going to give a summary of our full guidance. You can find more information at the documentation in the link. Let's start with good. We provide DirectX APIs to get access to the data that Windows has about the user's HDR display. DirectX combines data from multiple sources, including EDID, display ID, color profiles, external calibration apps, etc. And it rationalizes them to give you a single best known data set. For those displays that don't come with accurate data, we are working on a system calibration app that the user can run, and the data is then exposed by the same system APIs. This app has already shipped on Xbox and is coming to Windows. A critical concept that's particularly relevant to PCs is that your display's HDR capabilities can change at any time. This could be because your user has moved their game between different monitors, because they're on a laptop or another device with power-saving modes, or even because the room has gotten brighter or darker, changing the viewing conditions. Use our APIs to detect these changes and adapt your game's rendering to the new state of the display. This adaptation process is called display mapping, or sometimes tone mapping. Display mapping is its own enormous topic, and our docs have sample code and information about Windows inbox HDR tone mapper APIs. Okay, let's quickly look at some code examples. There are two display capability APIs you can use. The first option uses DXGI and integrates directly into your game's render loop. First, use the DXGI factory to check if the display state has changed. You get a new DXGI output and a descriptor. And from there, you have all the information that you need, including minimum and maximum luminance and color primaries. The second option is a Windows Runtime API. It's a little more flexible, but today it's only available for universal Windows apps. We provide an event handler called Advanced Color Info Changed. You implement your event handler and then grab the Advanced Color Info object. And from there, the same information is available. Okay, let's move on to better. This guarantees that for any display, whether it's calibrated or not, your game still has access to the most important subset of display color information. That subset is what we call the safe luminance rendering range. To help explain what that means, let's look at this diagram. I've plotted out a bunch of measurements from an actual HDR display. The x-axis is the luminance of the color values your game is rendering, measured in nits. And the y-axis represents the photons that the display is actually outputting, also in nits. As you can see, the relationship isn't linear. There is a minimum and maximum point at which the display just can't get any brighter or darker, and so it saturates or clips your game's colors. So your game needs to restrict its rendering to this safe range and never exceed the minimum and maximum luminance. Here's an example of a simulated image of an outdoor HDR scene that visualizes what clipping looks like. You can see in the upper left corner, we've lost all of the details in the sun and clouds. Similarly, in the lower left corner, we've lost detail in those rocks. Let's show you an example of how to implement basic calibration. This is exactly what our system calibration app is doing. As I mentioned earlier, it's shipping today on Xbox One and later, and we're working on bringing it to Windows. Our system calibration app follows the HDR Gaming Interest Group's guidelines. It shows 3 test patterns to measure minimum luminance, maximum luminance 10% frame, and maximum luminance 100% frame. For each test, we render a checkerboard or alternating pattern of squares. When measuring maximum luminance, half of the squares on this checkerboard are at 10,000 nits, which is the maximum valid HDR signal. The other squares, the user adjusts the brightness to be brighter or darker until they are visually indistinguishable from the max signal squares. And for minimum luminance, the user is instead comparing to 0 nits or fully black. A best practice is to give the user clear instructions that don't get bogged down in technical details and show them examples for what both success and failure look like. And finally, best. We have two pieces of guidance here. First, you might have noticed that the previous basic calibration steps only affect the extreme highlights and shadows in your game. But users are going to want to control how the midtones appear, really the vast majority of your game's content. In the next slides, we'll cover 3 additional color controls that you should implement. Now, the other best practice is to not just show a test pattern, but to let users preview their adjustments on either a pre-rendered screenshot or a live in-engine game scene. For example, what if you have a stealth game where the character is sneaking around in very dark environments? In this case, when your user performs display calibration, your game might respond very differently than a generic test pattern such as the ones I showed previously. Let's dive into the additional color controls. The first one is paper white brightness. This is a concept that's somewhat unique to HDR games. Paper white literally means how bright a piece of paper or other diffuse white content appears in your game. It's implemented as a multiplier in linear gamma. Paper white is really important to implement because a user's preference will change depending on how bright their room is at the time they're playing. And if you're familiar with the Windows 10 settings app, it has an HDR brightness balance setting. This is doing exactly the same kind of gain adjustment, but for windowed SDR apps. The second adjustment is contrast, and this behaves mostly the same as in SDR games. You can tune contrast to preserve more details in shadows or highlights in a scene. And this is implemented with a power or gamma function. The final adjustment is saturation, which is also a familiar concept from SDR games. This adjusts how rich or vivid your colors appear, and this is implemented with a color matrix. The second part is showing an in-game preview of your HDR calibration and adjustments. We're going to use Gears 5 as our example, which does an excellent job of providing a ton of control and information to the user, but still keeping things very clear and actionable. Gears actually shows 4 different preview scenes. 3 are screenshots and 1 is a live in-engine scene. And these reflect the variety of environments and content in the game. As in the system calibration example, it gives very clear and prescriptive guidance for what users should do and look for. Now, wherever possible, you should show the numerical value for any adjustment. This makes it easier for users to replicate those adjustments on other systems. And if those adjustments are measured in real-world units, such as nits, use those units, because this can be more intuitive for experienced users. All right, now on to our final topic for the session, auto HDR. Everything I've talked about up until now has been building native HDR implementations into your game. Auto HDR, on the other hand, takes an existing unmodified SDR game and enhances its colors to use both HDR brightness and HDR color gamut. For gamers, this is an awesome free visual upgrade. I've already purchased my game, and now suddenly it looks more rich and more vivid on my HDR display. And for game devs, you get many of the benefits of HDR on your already shipped games without needing any modifications to your code or your art assets. Of course, while auto HDR provides an impressive visual experience, it's not a replacement for building your own HDR implementation. You're always going to get the most artistic control and image quality by doing it yourself and following our guidance. Okay, I'm excited because we finally got into the demo. I want to show you just what auto HDR looks like. Now, unfortunately, it's impossible to accurately represent the benefits of HDR when showing an SDR video stream. So I'm going to do the next best thing with a visualization of all the colors that auto HDR gives you that SDR can't reproduce. This is an in-engine cutscene from the opening of Gears 5's Hivebusters expansion, which came out just at the end of last year. On the left side of the video is the original SDR, and on the right side is the heat map visualization of Auto HDR. Everywhere you can see colors on the right side, it means that Auto HDR is rendering those pixels with HDR luminance and is enhancing the original SDR image. Now, this enhancement is much more than a simple upscaling of colors. Auto HDR uses a machine-learned method that was trained on billions of pixels of HDR game data. Just like good quality native HDR, Auto HDR isn't simply about making everything brighter. You'll notice that it doesn't affect the appearance of most of the objects, such as people or things with diffuse surfaces. Instead, Auto HDR focuses on enhancing the highlights and shadows in the scene, most visibly the explosions and flashes of light as this plane flies through the storm. So this video isn't quite as good as seeing Auto HDR live in person, but hopefully it lets you visualize what kinds of enhancements Auto HDR provides and where it makes the most difference. We also have a version of this video that shows Auto HDR in its original colors. You can find it at this YouTube link. Of course, your device must support native HDR YouTube video playback to see the proper effect. Otherwise, both sides are going to look very similar since YouTube will be tone mapping back down to SDR. Now, if you've played Gears 5 before, you might be asking, hey, wait a second, Simon. Gears 5 natively supports HDR. Why does it need Auto HDR? And you're absolutely right. Gears 5 has an excellent native HDR implementation. And so no real user is actually going to be running it with Auto HDR. Instead, the reason why I've used Gears for my demo is so that we can directly compare Auto HDR versus high-quality native HDR. Here, I've taken a single frame of the previous cutscene with native HDR on the left and Auto HDR on the right. A heat map is a pretty crude way to visualize differences, but even so, you can clearly see things like the native HDR rendering a higher peak luminance with the volcano's flames. And it preserves more details in bright areas like these clouds. Here's a second frame. And we can see that the metallic surface of the helmet once again has more detail with native HDR. And then the glowing patches on their flight suit are significantly brighter. Okay, back to normal color images. So as you may know, Auto HDR first shipped with our latest generation consoles, Series S and Series X. Xbox has a long-standing tradition of enhancing the visuals and gameplay of your existing titles. Depending on the game, you can get unlocked frame rates, widescreen support, HD and 4K resolution, quick resume, and now high dynamic range. Auto HDR is enabled by default for all back-compat titles, except for cases where we know the game won't benefit from the feature. And we've been really, really happy with the consumer response to Auto HDR on Xbox so far. The obvious question was, can I get this on Windows? Here on the DirectX team, our goal is to take cutting-edge technologies such as DirectX 12 Ultimate and Direct Storage and provide a unified platform across PC and Xbox so that all of our gamers can benefit. So it was really exciting when we announced earlier this year that Auto HDR is coming to Windows. You can find all of the details on our blog. We support any recent game running DirectX 11 or 12. This encompasses the vast majority of gaming hours spent on Windows. And the best news is that you can try it out today by signing up for the Windows Insider program and joining the dev channel. You'll need the same basic system requirements as native HDR. This includes an HDR-capable display, GPU, and driver. And you'll need to turn HDR on first in settings. As a developer, you're probably wondering, how does Auto HDR work and what kind of impact will it have on my game? In a nutshell, Auto HDR on Windows is implemented as a post-process pixel shader that runs on your game's swap chain at present time. This allows us to run on every GPU architecture that supports HDR. We use swap buffer information, such as pixel format, to determine if your game is eligible for Auto HDR. Running as a shader does mean that there is a small but measurable performance impact on both your GPU render time and the allocation that's needed for an additional HDR swap buffer. The render time overhead is mostly independent of your game's workload and instead scales with your resolution. On Windows, our philosophy is to always give gamers control over how their system behaves. Therefore, in addition to the operating system's eligibility checks, gamers can turn off Auto HDR on any app by accessing the advanced graphics settings. And just as a reminder, an optimized native HDR game can integrate the HDR display mapping into its final output shader and avoid the overhead that auto HDR incurs. We consider the underlying auto HDR decompressor. We trained auto HDR on billions of pixels of HDR game output. This allows us to recover the color data that has been compressed by modern games' internal tone mappers. Depending on your display's capabilities, auto HDR can expand your game's SDR colors to target up to 1,000 nits and the DCI P3 color gamut. I talked earlier about how we tuned auto HDR to minimize the impact on your game's color grading and artistic intent. We've done extensive testing, and we think the vast majority of games will look better. For example, natural or photorealistic lighting styles work really well with the algorithm. On the other hand, some non-photorealistic styles may have unexpected results. For example, if your game has a visual style that resembles a graphic novel and it has a lot of elements rendered at full light. And of course, you always retain full control over building HDR directly into your game. And with that, we're at the end. So what did we learn today? First, HDR is the future of visually immersive experiences, and there's never been a better time to build an HDR game to target the rapidly growing PC market. Second, Microsoft is working with the ecosystem to bring you higher quality and more consistent HDR displays. Third, we've shown you techniques for how to get the maximum image quality on whatever display you're running on. And finally, Auto HDR provides an amazing visual upgrade for existing SDR games, but of course, ultimate control comes from building HDR support yourself. For your viewing pleasure, here are all of the external links and videos that I've referred to in this session, and you can also find these links in the session resources. And as one final note, I want to give a personal thank you to everyone who's a part of this incredible gaming industry and community. This last year has been so challenging in so many different ways. But for me and many of my friends and colleagues, video games have been a rare beacon of hope. They've entertained us, they've comforted us, and most importantly, they've connected us with our loved ones, no matter where in the world we happen to be. So from the bottom of my heart, thank you for being so awesome, and may we meet each other again on the other side.